Hello and welcome to Oracle's Day 1 and Beyond hands-on training series. My name is Dion Locklear and I'm a cloud engineer here at Oracle with 4 years of experience working with cloud-based infrastructure and platform technologies. Today we're going to demo some of the more marquee features in Oracle's latest long-term support database release, the Autonomous AI Database. Those features include AI vector search, JSON relational duality, SQL property graphs, and SQL domains. Let's dive in. To start, navigate to livelabs.oracle.com and search for Oracle AI Database 26 AI new features. From there, we'll go ahead and click the Start button, run on LiveLabs Sandbox, we'll consent to receive emails from LiveLab, and then we'll submit our reservation. Afterwards, we'll go to My Reservations, and we'll launch our workshop. From here, we'll navigate to the upper left-hand corner, View Login Info. From our reservation information, we'll grab our password, take note of our username, and we'll launch OCI. We'll leave the identity domain as default and click Next. Verify that this is the correct user, and go ahead and paste your password. You will be prompted to change your password. Paste it once again, and again. I like to append a 1. And now we have a new password. With that, we can get started.
Once you're logged in, you'll see the OCI console homepage. The first lab that we're going to explore is AI vector search. Vectors are how we represent the semantic content or the implied meaning of unstructured data, so things like documents, videos, or images. In this lab, you'll learn what vectors are and how they're used in AI applications. We'll cover the creation of vector tables, perform basic DDL or data definition language operations, and dive into similarity search using some of the new SQL functions in Oracle Database 23 AI. The first thing we need to do is navigate to our autonomous database instance and open our SQL web interface. You can do so by going to the Recently Created tab and finding your autonomous instance here. Once on your autonomous database homepage, navigate up to the top dropdown and hit Database Actions and select SQL. Once our SQL interface loads, you'll see that it's broken up into 3 main sections. Along the left-hand side, we can find our database tables, objects, and files that we can work with. In the top section, this is where our SQL commands will be written and executed from. And finally, in the bottom section, this will list the results or our SQL output. The first thing we'll do here is create a table with our new vector data type. We'll now run this as a script. And as you can see, our resulting output is shown in the bottom section of our SQL interface. Now let's add some data to our vector table and then query the table we just created to see the data we just inserted. The data we just entered is now shown in our SQL output section. We can also use regular DDL against our vectors, just as we'd expect. So now let's update the vector table we just created. In our output section, you will notice that the first row in our vector table has now been updated to 0. We can also delete rows with vectors just as we'd expect. As you can now see, the third row in our vector table has been removed. Now let's go another level deep and discuss dimensionality and formats. So what is dimensionality? Let's think of it in relation to how we perceive the world around us. We exist in a world of 3 dimensions: height, length, and width. Vectors contain several numbers that denote specific features of your unstructured data, such as a particular image, typically ranging from sets of a few hundred to a couple of thousand, with each number signifying a particular feature of the item in question. For example, a vector of 1, 2, 3, 4, 5, 6 has 6 dimensions. The Oracle database currently allows you to use up to 64,000 dimensions when storing vectors. If we refer back to our vector column, you may notice that we didn't set a dimensionality. You can optionally define the number of dimensions while creating a table, and you can also define the number format of the vector. For example, if we paste the following statement, this means that the vector has 3 dimensions of type float 32. Now let's add some data. As you can see, we inserted some data into our vector values here. Now let's take a look at what happens if we try to add a vector that has more or less than 3 dimensions. If you haven't already guessed, we're going to see an error. By defining the number of dimensions, we're effectively creating a check constraint. We can also create multiple vectors in one table and define them with different formats and dimensions. To give a real-world example, let's imagine that we worked at a company called Movie Streams, a movie streaming company where customers sign into an application and can access thousands of movies and TV shows for a monthly subscription. We'll create 3 tables: customers, movies, and ratings. Now that we have our tables, we can now add data. If you didn't already notice, we left our vector column null, so let's go ahead and update that now. Now that we have our tables and vectors populated, let's imagine that we've been tasked with creating a new feature that allows customers to search for movies based on natural language. To create this, we would first need to map speech to text using a speech recognition system. For the sake of time, we'll create a table and load in some pre-vectorized questions. Now we can search for movies based on our customers' questions. For example, we could take the question, "Can you suggest movies that explore dark or serious themes but still include humor?" The ID equals 2 in our statement here refers to the ID of the question that we inserted in the table in the previous step. As you can see, we get a list of movies that fit that criteria. Now, let's try where the ID equals 4, which should suggest movies that your teenage niece may enjoy. As you can see these movies listed that fit that criteria. And finally, let's try where the ID equals 3, which should suggest some feel-good movies. This wraps up the vector search portion of the demonstrations, and we can now clean up what we've done by dropping our tables. Now let's move on to JSON duality views, which allows for the seamless integration between the relational and JSON data models. This feature provides the strengths of both approaches while allowing you to easily manipulate data in either model. During this lab, you will learn how to create, query, and update JSON relational duality views using both SQL and REST. So let's create some tables to use in this lab, and I'll paste the following SQL command. In this example, we're creating a simple conference schedule management system. So let's now create a couple of duality views for our conference schedule system. We're starting with the most simple form, a JSON document representation of a single relational table. We will do this for the attendees and the speakers. Using duality views, data is stored in relational tables in a highly efficient, normalized format, but is accessed by apps in the form of JSON documents. As you can see, these duality views are a one-to-one representation of your relational tables. Now let's discuss duality views on multiple tables. Application objects are commonly more complex than simple relational tables, meaning those are spawning multiple tables when being used within an application. Let's now do exactly that for the duality view representation of the schedules. A schedule object will comprise of the attendee information, the schedule for an individual attendee, and the detailed information about a session, including the speaker information. With the relational tables and duality views in place, let's use JSON and relational interchangeably for a single table duality view. First, let's look at the attendee information. We inserted data into our relational tables before, so let's now add another attendee using the duality view. It will automatically be stored in the underlying relational storage. As you can see, one of the many benefits of using duality views is that there's no data duplication. All changes are reflected immediately in the underlying relational storage. Let's now switch to scheduled document. If we notice here, there's a typo in one of the speaker's names. It's supposed to be BEDA and not BODO, and it impacts all our attendee schedules that go to one of Beta's sessions. We need to fix this immediately. let's check quickly whether we did it right. We can see now that the speaker's name is now updated correctly. But what about the individual schedules of the attendees? Let's go ahead and check that now. This is another major benefit of JSON duality views. Unlike JSON collections that embed all the information of an object within a single document, causing data duplication, duality views benefit from the underlying relational storage. The information about a speaker is stored once, and any change is automatically changed for all related documents. Next, let's discuss fine-grained document control. While we allow you to see the speakers here, we only allow you to do a subset of data changes to it. Let's experience this firsthand. As you can see, you're not allowed to change the rating of an existing speaker. Let's now move on to schema flexibility. One of the big value propositions of JSON documents is schema flexibility. You do not have to necessarily know all attributes and structures of your documents, and those will most likely change over time anyways. Duality views give you this flexibility with their flex fields. The attendee duality view was defined with the schema flexibility, so we can add any attribute to our attendee documents. Any attribute that is not explicitly mapped to a relational column will simply be stored in the flex column, which is of type JSON object. Let's try this now. As you can see, we added a new attribute that is not mapped to any specific column without any problems. Checking the relational underlying table for this duality view will show you where this information ended up in the flex field extras. Finally, let's discuss generated columns and fields. So far, our duality views have mapped to the columns in our base relational model, exposing the information in the relational schema as JSON documents. However, there is more that you can do with duality views. Often, derived information from existing data is necessary to complete or augment information. This is very easily doable with duality views. In our example, you not only want to show the speaker information with all their sessions, but you also want to know the total amount of sessions that a speaker is actually signed up for. We can use generated fields to add additional data that is derived from other information in our duality view. Let's change the definition of our duality view as follows. As you can see, we're able to derive the number of sessions for this particular speaker. We can clean up from the lab by dropping our tables at this point, and we're going to move on to the next topic. In this next lab, you will learn about the new SQL property graph feature. Property graphs enable you to define graph structures inside of the database and simplifies graph data analysis using SQL and PGQ queries. By the end, you will understand how to create property graphs, query them using SQL or PGQ, and visualize the relationships within your data. Let's start by creating our user for this lab. We'll call our user DB23AI and grant the user the developer role as well as the graph developer role. Now let's sign in as our new user. So we're going to click on the admin profile in the top right hand corner and sign out. And we're going to sign in as the user we just created. We're going to click SQL to open the SQL editor. And now we can create some tables for our demo. We'll create a people and relationship table, which will be our vertices and edges of the graph. The property graphs are stored as metadata inside of the database, meaning they don't store the actual data. Rather, the data is still stored in the underlying objects, and we use the SQL PGQ syntax to interact with the property graphs. You may ask yourself, why not do this in SQL? The short answer is you can. However, it may not be as simple. Modeling graphs inside of the database using SQL can be difficult and cumbersome and could require complex SQL code to accurately represent and query all aspects of a graph. This is where property graphs come in. Property graphs make the whole process of working with interconnected data, like identifying influencers in a social network, predicting trends and customer behavior, discovering relationships based on pattern matching, and much more, by providing a more natural and efficient way to model and query them. Let's take a look at how to create property graphs and query them using the SQL/PGQ extension. First, we'll create a property graph that models the relationship between customers. A couple of things to point out here. A vertex represents our customers table. Edges represent how customers are connected. And finally, our edges table has a source key and destination key, representing the connection between two people. Now we're going to take a look at Graph Studio. So we're going to click the hamburger menu in the top left-hand corner and select Graph Studio. And again, here we'll log in using the user we created. Once we're logged in inside Graph Studio, we're going to click on Notebooks. We'll hit Create in the top right-hand corner and give our notebook a name. I'll go with Customer Graph. If you get a pop-up for a compute environment, just ignore this and click Close in the bottom right-hand corner. Since we haven't set up the compute server and don't need it for this lab, you may get an error saying it wasn't able to create, but you can go ahead and close those messages. Next, we're going to hover over the middle of the text box and click Add SQL Paragraph. We can now query this graph using the new SQL PGQ extension in Oracle Database 23AI. The following query will look for customers starting at the vertices Jim Brown and then his friends within 1 to 3 hops. The important step here is that the match clause, which allows us to define the nodes we are looking for in our graph. We indicate we are starting from V1. We then apply a filter to select Jim Brown. We tell it to traverse the graph in a single direction, navigating all edges that are marked friends from 1 to 3 hops. We finally tell the query to return the paths for the hops that match the query. If we add new customers and relationships, they are made a part of the graph and can be queried instantly. Next, we'll add the customer relationship into the next cell and run the query. Finally, we can also update the first cell and change friend to cousin. In this short lab, we've looked at SQL property graphs and SQL/PGQ in Oracle Database 23 AI. We've learned how to create property graphs from existing tables, query these graphs to discover relationships, and prepare data for visualization. Next, we're going to take a look at SQL domains. Data use case domains play a crucial role in data integrity and consistency within database applications. Data use case domains provide consistent metadata for development, analytics, and ETL applications and tools, helping to ensure data consistency and validation throughout the schema. In this lab, we will explore data use case domains in Oracle Database 23 AI, covering single column data use case domains, multi column data use case domains, flexible data use case domains, and enumeration use case domains. Through these examples, you will gain an understanding of how data use case domains can be defined, applied, and used to maintain data quality. Let's start by creating a single column domain for storing product prices. We will enforce a constraint to ensure that prices are positive numbers. Next, we'll create a multi-column domain to represent geographical coordinates. This domain will enforce constraints on latitude and longitude values. Finally, for the flexible domain, let's consider a scenario where we want to store contact information for individuals. We'll create a data use case domain for different types of contacts and dynamically select the appropriate domain based on the contact type. Oracle Database 23 AI also has some pre-created data use case domains that we can use, with many more on the way. As you can see here is a list of all the pre-created data domains provided by the system. Now let's create some tables and apply our data use case domains. Now we can insert some sample data into the created tables to test domain constraints. If you notice, the widget will get inserted into our table and the gadget will fail. This is because it fails our constraint of only positive numbers in the price domain. Now, we can also insert into our multi-column domain table and our flexible domain table. Again, our first insert into the locations table will fail here because our latitude is greater than 90, but our second insert statement will pass because the constraints are correct. We can also create enumeration use case domains. These are a list of names with an associated list of values. If we don't manually define the list ourselves, the ordering starts from 1. We can also define the values ourselves. We can use both numbers or string values here. As with other domains, we can also use the enumeration domains in our tables. It's important to note that automatically assigned numeration values are just an ordered list, meaning there's no enforced assigned order. If we change an item, we could end up corrupting our data. A simple way to avoid this is by assigning the value ourselves. This way, the order statuses are consistently defined and immune to logical corruption, even if new statuses are added or the order changes in the enumeration domain.
This concludes today's Oracle Day 1 and Beyond hands-on training session over AI Autonomous Database. If you'd like to learn more or get exposure to more OCI services, please visit livelabs.oracle.com. We appreciate your time and thank you.